So, colleagues, let's start. I think we have enough number of participants that was already joined. Good morning, good afternoon to everybody. On behalf of Asian Development Bank and MRC Turkey, I would like to warmly welcome all of you to the second webinar of the Technical Assistance Project in terms of the high-level transmission technologies that is being executed in Cambodia, Tajikistan, and Uzbekistan. And I think today we have already representatives from the system operators, the ministries, and also other participants from different companies. So thank you for your time, for taking time to participate. I mean, before we start, I would like to share a few, let's say, information about the webinar. In this Zoom, you can select your language preference. We have the English-Russian simultaneous interpretation that we will be going on. And we have a Q&A box which you can submit your questions at any time so that our speakers can respond to them. After the, let's say, speakers' presentations, you can also direct the, let's say, questions by requesting as well. And also, we will be sharing the slides and the recording to the participants after this presentation. And we have a 90 minutes agenda for today in terms of the webinar. And we will be starting with the welcome of the Atsu, our colleague, senior energy specialist from ADB. And then we will be proceeding with Mevlut's presentation in terms of the constraints, voltage, reactive power, and strength of the power system. Mufid will be more concentrating on the different, let's say, solutions in terms of supporting the transmission system operators for their different voltage and reactive power issues. And then Gilles will be moving on the real cases on the weak and inverter dominated grids. And afterwards, we will be having a moderated discussion. So any further Q&As that you cannot ask during the presentations, you can leave it to the end, but I suggest you not to do so. So those are the highlights from the today's agenda. Maybe I can leave the floor to Atsu for his welcoming remarks. Atsu.
Thank you very much, Goham. Okay, so good afternoon, Excellencies, distinguished guests, and colleagues and friends, especially from the participation from the Cambodia, Tajikistan, and Uzbekistan. Once again, my name is Atsu from ADB. I am doing the project officer of this technical assistance. First of all, thank you very much, MRC Turkey, for their organizing this webinar, second webinar. Thank you very much, everyone, for joining us today and for your continued interest in this webinar series on grid resilient technologies. I am pleased to welcome you to the second quarterly webinar under ADB's technical assistance on grid resilience. This work is supported by the High Level Technology Fund with the government of Japan as a single donor, and we are grateful for its continued support in bringing advanced technologies and international experience to our developing member countries. As the Gohan mentioned, following the feedback received from our first webinar in May, today's session focuses on high-level technologies for managing grid voltage. And this is a timely and important topic. As the recent widespread power outage in the Iberian Peninsula reminded us, voltage stability is a critical issue for power system operators, planners, and policymakers, and particularly as the share of renewable energy and inverter-based resources continue to grow. Of course, the voltage instability itself is not a new challenge. In large load centers, especially in major cities, voltage instability and voltage collapse have long been concerns that the power system operators must manage carefully. Without adequate countermeasures, such as the VAR compensators and other reactive power support technologies, the voltage stability constraints can limit transmission capacity and reduce system reliability. Today, we are fortunate to have eminent speakers from around the world who will share international best practices and practical lessons on strengthening grid resilience against voltage instability. I hope the knowledge exchange today will help system planners design future grids that remain stable, reliable, and resilient, even under higher shares of variable renewable energy and other inverter-based resources. With that, let me hand over the floor back to Mr. Goham, Project Director of MRC Turkey. Thank you. Over to you.
Thank you, Atsu. Well, before maybe proceeding with the technical presentation, I would like to take the liberty to spend some minutes in terms of how to allocate today's webinar into the broader context of this project and try to explain why we have chosen to dedicate an entire session to voltage and reactive management. As Atsu mentioned, that was one of the request both in our first webinar and in our workshop, Inception workshop in Tashkent. As for the colleagues who has joined, we have, let's say, executed the audience feedbacks in terms of what is the most important issues. So that was the, let's say, topic that has been selected in those interactions. And overall, this project is more about supporting the participating countries in preparing their transmission system for significantly higher shares of renewables, and at the same time maintain the secure and reliable and the strong and economical as well system operations. So it's more than let's say just simply connecting, putting more solar and wind generation into the system, as you all aware. As we are having more and more variable renewable sources, the nature of the power system is also changing a lot. I mean, historically, we were in the transmission system, we were connecting mainly the synchronous generation, and most of our issues were dominated by the N-1 reliability, thermal loading, and network expansion. So those were our main, let's say, issues historically. But today, the system operators are increasingly facing other issues and questions as well. And one of them is basically, will the system remain voltage stable under changing operating conditions? So where are the weakest bus bars of the network? How much reactive power reserve should be actually available, especially during the stressed hours, like peak demands or minimum loads or maximum renewable generation hours? And also other topics in terms of the fault levels. Will our fault levels remain sufficient for our protection systems to operate properly? And how the inverter-based resources will be contributing to the services that synchronous machines can provide, because that will be also one of the, let's say, important issues. And at the same time, we are trying to also solve the main dilemma of how the future investments will solve the actual engineering problem, rather than just simply adding more equipments. So those are the typical motivations of this technical assistance. So in that sense, our objective is not only to review the international best practice, but also develop a practical country-specific engineering recommendations which can support the future steps for each country. And today's webinar is one main important block within this process. So the knowledge that we are planning to share today will be supporting the detailed technical studies that will be following for each participating countries. And we will be, let's say, concentrating on plenty of different technologies as, let's say, first long list, and then we will be proceeding with the short listing of those for each country. And as you may remember, both in the Inception workshop and also the webinar, first webinar, the wide portfolio of high-level technologies that can support the modern transmission systems has been also presented. I mean, it was having a, let's say, wide portfolio from advanced reactive power devices, system strength solutions, flexibility, let's say, management, forecasting, monitoring, digital operational tools. So there were plenty of different high-level technologies that was discussed in those, let's say, discussions. And in the overall, let's say, positioning, this webinar is the top ranked topic out of the plenty of different system challenges that has been discussed before. And typically we are, let's say, trying to have a systematic in terms of how to, let's say, convert our recommendations, how to, let's say, start with the problem and how to develop the recommendations. So, first of all, for each country, we are at this stage to identify what is the actual binding constraints. So we are trying to get those, let's say, overall picture. And then we are defining what kind of services. So either as a, let's say, as a conventional ancillary services or some obligatory services, define the services that will be required for each country, and try to solve the identified problems in each country. And for that, we are, let's say, trying to shortlist which technologies will be best for that. And the next step for that is how it can be converted into an evidence-based and analytical study that will be, let's say, supporting the transmission system operations. So, these were the five technology pillars that we were discussing, and the webinar one was mostly also concentrating on the inertia and the frequency parts of the topics. And today we will be touching a few of the other, let's say, taxonomy items, but it will be main voltage and reactive power, let's say, context. And in the upcoming webinars, as Atsu said, we will be covering plenty of different, let's say, topics that will be also touching base the other topics as well. And before the poll, I can briefly also give introduction about our speakers today. Let me start with Mevlut. I mean, Mevlut is an ex-TSO guy, and he has many years of experience in Turkish TSO in terms of the transmission planning, power system analysis, grid operations, ancillary services, smart grid developments. Also, plenty of aspects he has been covering, and he is supporting also the project as one of the lead technical experts. Our second speaker is Mufid, and he's serving as a solutions architect, and he has extensive experience in utility technologies and grid modernization. So, I mean, throughout his career, he was working on translating the complex technical requirements into practical engineering solutions for utilities. So, he will be introducing the technology toolbox side per his experience in today's agenda. And our third speaker is Gilles, and he's an international recognized expert. For those who is following him on LinkedIn, he's posting, let's say, really robust material in terms of the new, let's say, phenomena that is being coming into our topic, our operations with the increasing inverter-based resources. So he's a power system dynamics and stability expert, and he has been supporting many system operators around the world to, let's say, improve their systems. So before leaving the floor to Mevlut for his presentation, I think we have a poll. So, we have a question? Okay. How will we get the questions? Colleagues, you are allowed to, for the colleagues who has raised hand, you are now allowed to talk. Please go ahead. Yun, Samedi. Okay. We don't hear anything from them. So let's move on. So we have a poll at this stage. Aisha, are you going to share the poll participation? Okay, let me stop my screen now. So I think you had the poll in front of you right now. So the first question is, which voltage condition represents your primary operational concern in your system? Whether it's the high voltage at the low load scenarios, especially night times, or low voltage at peak, or you have a varying characteristics in your system, or it's more about the more transient power quality phenomena like voltage sag, voltage dips, or like you are not monitoring your, let's say, voltage related parameters. That was about the first question. And second question is about the reactive power reserve or the voltage margin that you are, let's say, using in your control room in real time, whether you are doing it or not, because some system operators are having already implementing the tools for real-time visibility provision. Some of them are just managing it offline. Some of them are not even making any analytical studies, so you can select based on your existing practice. And let's wait 30 more seconds and then we will move. Okay, good. I think we have replies from more than half of our the participants, which is good. Probably the other half is not from the system operator. That might be the reason for not replying to the poll. I think the majority of the responses, around 60%, is more, let's say, having the, let's say, concerns of different operating regimes within the year. So based on the different timing of the year, both the at peak hours, the low voltage issues, and also at the low demand hours, there are high voltage issues. So majority of the, let's say, participants has responded like that. And also, I was a little bit surprised that we have not small, 20% of the participants has shared that they have also power quality issues, which is, let's say, also another key interpretation of the results. And for the second question, I think around 60%, which is a little bit surprising for me, of the control center, control room operators are right now having the real-time visibility in terms of the reactive power reserve, which is good. I was expecting a lower figure considering the fact that we have already discussed in the participating countries about the lack of such, let's say, systems in their control centers. Okay, so that was our first poll. Mevlut, the floor is yours. I'm gonna share my screen so that everybody can see the presentation as well.
Okay, are you going to share the presentation?
I think I did. It should be coming in a second.
Okay, thank you, Gökhan, for such presentation in brief. Today's topics, especially based on the reactive power regulations, voltage and constraints, and grid system strengths that we are experiencing in our grid operation recently. This is Mevlut, as introduced in the beginning. I'm ex-TSO guys, and today I'll try to explain, give some briefs regarding the problem and the new phenomena based on the reactive power or control of the reactive power, constraints, limitations on the grid operation. So we will try to identify what kind of issues we are facing recently with the emerging technologies, and which are mainly applicable to different types of topological grid operation, grid topology, and the generation fleet of the country is also dependent to this interfacing problem, also the consumption and emerging loads. So as we mentioned, based on our initial project member countries, we have 3 member countries in this project, and which are all specific topological structure and operational structures specific to each other. Also, they have some common, maybe probably the common operational structure, because since as Atsu mentioned, the voltage and reactive power controller stability is not a new issue, but it is an emerging issue for the last couple of decades, let's say, because in the past, as we are using the conventional generators in our grids, mainly hydraulic power plants or thermal power plants, let's say rotating machines, they are all synchronous generators and also providing the reactive reserve. They have large reactive reserves. They are also providing spinning reserve, also giving some active power regulation in case of any loss of or imbalance in the grid. And recently, in the last few decades, as we are all aware, we are replacing, even not replacing, we are adding new power plants based on VRE, we call it variable renewable integration energy resource. We are adding these in our fleets. In fact, the hydraulic power plants are not replaced, but the thermal power plants are replaced with this inverter-based generation due to some environmental constraints or aging. Even the existing hydro potential or the conventional potential is limited. Most of the TSOs trying to add up some renewable energy based on inverter-based generation. So there are 2 very, very basic and fundamental difference and evolving shapes in our reactive power reserve regarding these emerging generational loads. Switching or moving from conventional and synchronous generator to inverter-based generators makes the plant or grid operation a bit complicated, because as mentioned, it's a classical machine, rotating machine. It has some by nature natural response, like fault contribution or frequency response, some kind of damping torques or synchronizing torque in the grid. In case of an imbalance in generation and demand, the rotating inertia provides instant withstand or instant energy to keep the frequency in some level, which should be also provided in IBR type of generators, but it requires many complicated intentional control actions, which is available on most of the data sheets, but we should also keep them on site and also test on site with these parameters. Maybe the next session, my colleague Mifid will also explain the new technology facts, more practical solutions and their implementation maybe on the grid. So regarding the next one, Gökhan can move, Ayşe can move to next. Yeah. Next slide, please. Well, not the previous one, maybe about the capability and the contribution. Yeah, as I mentioned, the synchronous generator itself, the classical one, has its own natural capability and the contribution. If we just install and set these machines with their own default values, so it supports our grids in terms of reactive power, fault contribution, and rotating mass in terms of active power. So it may have many features which is built in already. Once we switch to inverter-based generation in the renewable energy sites, say wind or solar power plant, they are all based on or coupled to grids via the inverter systems. In terms of technological design and technical data sheets on the pages and documentations, we may have many features just copying or trying to behave like the synchronous machine by their design, like maybe synthetic inertia, automatic voltage regulators, even some fault contribution in a limited scope. But these features are very specific and specific features, first to be specified in some technical codes, then during the manufacturing and sizing, they should be inherently implemented in the design. And finally, even we install or we import, we buy some couple of machines based on these features, we should also activate these features in a correct manner. So this stage process is not only the definition of the specification on the manufacturing side, but also as a TSO during commissioning or before commissioning, we should set and also monitor these features. And thanks to PMU type, very fast and high-level technology monitoring systems, even during the regular events in the grid, say we have a couple of times line faults in the grid per 100 kilometers. This is a typical ratio for TSO operation. So if there's a fault nearby the new type power plants, inverter-based power plants, and once we get or installed our PMU WAMS type devices, we can also monitor this power plant response if it is complied with the technical requirements in the beginning that we specified or not. So these are technological systems automatically captures the response, and we can also check if we have really real practical reactive reserve or response service in these highly dominated VRE regions. As we had the poll a couple of minutes ago, so I think the ratio is not less. I mean, most of the TSU have real reactive power margin reserve monitoring in real time. Yeah, this could be in steady state operation. In fact, to be honest, as based on our own TSO experience, so during the real time operation, we can also get these reactive power margin. So if we switch on some additional shunt compensation, or if the consumption, the load has more reactive demand, these power plants or these resources may support this reactive power from our reserves. But the critical point is, what if in case of any fault, any transient condition, do we have still enough margin or transient margin, or even these systems, the machines can support, provide their requirement during transient, which only persists a couple of seconds. So it's not a very easy task to monitor also these transient capacities or margin with these typical conventional SCADA systems, say, which has some couple of second interval data transmit. So in this aspect, we may also switch to wide area measurement system or phasor measurement systems, which also monitors and takes the power quality analysis, also monitors this transient response. So it's one of the technological practical way of also monitoring the reserve in our grid in real time, if reactive power is enough or response is enough during a practical or real transient case. So the main gap between the conventional power plants and the IBR type inverter-based power plants, let's call VRE maybe, is mainly not only the capacity, but the contribution and the settings on the side. So these 2 points may be more practical topic to be monitored and implemented on site for the TSOs interested in these issues. And once we move to next page, the main one of the issue that can be interfaced during grid monitoring or grid scanning. Next slide, please, Ayşe. The PV curves that we would like to discuss or give some notes.
Mevlüt, we are seeing the PV curve slides. I think it's coming slower to you.
Sorry. Okay, so you already see the PV curves, right? So okay, so opening my other screen. So let me proceed with that. Yeah, the PV curves is very practical. In fact, way of scanning the strength of the grid. So normally in a complicated grid or an emerging grid, it may be not easy or practical in short time to represent the grid model. That's another issue for planners or dispatchers also, because to get the practical model in a valid condition, we should first take all the database, the data sheets, test results, and many way of documentation, and we should transfer these data to our software. So it's not easy task, to be honest, to scan and make these dynamic or transient analysis very frequently in an automatic way. But there are some incremental analysis approach, which is also practical and analytically proven, used in TSOs, make an incremental scanning approach. So PV and QV curves are one of these like short circuit assessments. So we just do some incremental load flow analysis in some weak buses or sample buses, or even in all buses, main buses. Once you have implemented load flow with incremental active power solution, we can also plot this voltage variation in the grid depending on the incremental load active power, which gives critical and valuable insight on this bus bar. Means that if you absorb additional incremental power from the bus bar, you are getting approach the edge point, and this edge point is normally theoretically the unstable part of the grid operational points, and it is really dependent to M-1 also. So number of lines connected to substation is also critical. So we can also make some scanning, try or implement M-1 analysis, and if the curve is jumped relatively too much, it means that even the M-1 in your typical analysis, M-1 load flow converge, but it says that during any transients, you have very little margin to keep this to move or step from the M- pre-fault condition to the post-fault condition in real cases. I mean, the load flow may converge. It's a simulation. It just simulates the 2 points shown on the plot, edge points. So numerically, they are imbalanced and converged. So the convergence and the error is zero practically. But transition from one point to another point in transient domain, it may require some transient analysis, or you can just scan and image this transition critical unstable point via very simplified load flow solutions called as PV curves. Similar to PV curves, we have also QV curves, which also says similar approach. The voltage stability of the network also. I mean, we have many voltage stability issues given in our interface in our grid operation. It depends on the topological structure of the specific grid itself. For example, in Tajikistan, as we have many irrigation pumps spread over the country, so long medium voltage feeders and irrigation pumps may cause voltage stall, which also have some regional loss of network due to limited reactive power. Or we may have also some large loads, fluctuating loads, also operating in the grid, specific to localized to specific region. If there's a heavy industry kind of loads or some huge loads, the reactive power jump may also give some voltage stability issues and loss of regional part of the network is also possible. And again, the voltage and reactive power stability marginal scanning is represented by the QV curves. We have some operational stable points in the load flow results, and we can also try the n-1 to see the incremental or relative jump if the bus bar or substation at that region is strong enough or not. So for the point-wise load flow solution, or we may converge this load flow solution, so it's everything goes okay, but the load flow itself only does not give some insight regarding these transients based on the reactive power regulation. So in order to keep this curve shift up level, sometimes fixed capacitors may have some solution, but fixed capacitors only shift the curve. We also want to reshape the curve by adding some dynamic reactive compensation, which also brings some reshaping of the curve, so we can shift the point, so we can increase our reactive power margin in case of instability transient event in the real-time operation of the grid. So this reactive support, dynamic reactive support, can be supplied with the synchronous generators, which is already available on the most of the grids, and mainly hydraulic power plants or thermal power plants. And once we add the additional or replace the thermal powers or add new IBR type machines, so we should also check the reactive power dynamic support of these machines, as I mentioned in the beginning, not only on the data sheets or capability, we should also check on the commissioning tests or design documentation, or even in the real faults, we should check, we may check these response if they are enough or not, or if they are capable of giving their contribution specified in the document, specified in the data sheet. Let's take another two-sided problem, the line charging, the out of phase 180-degree out of phase reactive power problem in a typical grid, the night surplus and the peak deficit. So the long lines, I think it is the case for Uzbekistan in the western part of the country. So we have long lines in the light load case. Even for the other countries may have similar approach or interfacing problem, because the daily load curves may have some typical daily load curves, which the consumption could be less in the night or in the early morning, and we have the long lines bringing the supply from far ends, and if they are kind of PV, and if you don't have any reactive support from the PV called as Q at night, let's say, because the PV plants, if they are not operating during the night, if there is no load, you cannot, or we cannot de-energize this line, causing the surplus reactive power, because the de-energizing the line solves the excess reactive power, but it also separates island the PV plants from the grid. So the case is, if you just explain from a practical real case from our TSO experience, let's explain. We have strong or large PV plants far from the grid, main grid, or wind power plants, and due to its size and capacity, as a first stage, where they are just integrated from the 400 kV or main network, because the capacity is a couple of 100 megawatts. But there's a case that if there's a half of the day during the night, the PV plants are not generating, and they are not operating at Q at night mode, but we should also still keep the line energized. That's the problem here. And the very practical and the first solution is putting some switch shunt reactor in these nodes. But then we interface with the voltage jump problem. So sizing the switch shunt reactors or making it dynamic variable compensation is a trade-off. So depending on the short circuit power on the grid connection point, we can either select the shunt reactors or STATCOM or SVC. So we have typical different type of technologies giving not same but the similar results, or serving for the similar purpose, but the method and approach is different, cost is different, and technology is different. So the main problem or main issue is based on the reactive power and the voltage regulation, but the solution pathway could be different depending on the topology, network topology itself, which is also related to country-specific generation fleet, daily load curves, and the geographical spread of the network in the country. So the line charging is excess charging is a problem in the night with the long lines, especially in the high voltage lines, or even with medium range cables. We may have excess charging reactive power here. And during the day peak hours, also vice versa, we have also a similar problem in the negative voltage depress. So the absorption of too much active power, also some reactive power, the line or the network can be loaded over the surge impedance loading. So there's a very primitive, basic but good indicator for the lines. Most of our TSO colleagues are aware of that. So we have the natural loadings of the lines, and surge impedance loading is called also. So if the network is averagely loaded over these values, so we need reactive power support here. Or if the loading is less than this, critical natural loading, so we need some shunt compensation to absorb the excess reactive power at this point. So since the daily load curve and the generation fleet is changing in a typical daily operation in both axes of the both axes, even from one side to east to west or vice versa in a day, or if some hydraulic fluid may operate a couple of hours as a peaking, and the remaining part, the VREs may contribute. So not only the load patterns, also the generation patterns are also changing, and a couple of times in a day. So which makes the switching shunt or switching compensation not practical to catch these quick variance during the operational stage. Then we may also consider at this stage some roughly some percentage with fixed compensation systems, which is easy and inexpensive, but after some level of point, the varying part should be also compensated via some dynamic tools like SVCs or STATCOMs, or the power plants in operation should also contribute this dynamic voltage or reactive power contribution in these conditions. And specific to, as I mentioned, some fault-induced delays, delayed voltage recovery, also another issue and problem in the countries or in the networks which has many motor loads with connected long lines in the grid, because motor itself during starting or stall, it absorbs roughly say 6 times or 5 times the rated current as a reactive power. And in the urban or suburb, in the far rural areas, if we have many irrigation pumps or similar motor loads, we have also a serious problem. The motors can operate in the steady state, so we are supplying these loads in the daily operation. But if there's any fault, even it's a temporary fault, just cleared in a couple of 100 milliseconds, once the voltage dip is propagated towards these motor loads, they stall or they absorb a couple of times more than the rated current reactive power during the voltage dip. And since we lose the voltage stability or reactive reserve here, they cannot recover again, or it takes a couple of seconds to recover because the voltage buildup is maybe slow. And it is also related to the voltage strength of the grid at that point that I can mention a couple of minutes ago. So the voltage strength here, not only the short circuit power, but also the QV curve edge points. Because even we have a short circuit power here, maybe there's a huge power plants. If the reactive power, the short time overloading of the reactive power of the system is not high enough, so the only short circuit power does not guarantee such dynamic or soul recovering voltage issues in the grid. So we both need short circuit power strength and reactive reserve, fast reactive reserve at these problematic areas dominated with the motor load and connected to the long lines. And as I mentioned, strong grid and the voltage, keeping the voltage in a operational value issue. So the strong grid, what does strong grid means here? It is strong in terms of voltage capability. So the first item is the short circuit ratio. If I have a high short circuit ratio, it means that I have many synchronous generators nearby. So if any fault occurs at the region, the point with the faulted bus bar is voltage is depressed, but the surrounded or remaining bus bars voltage could be far over zero, practically zero voltage. I mean, the voltage is not depressed too much if the grid is strong at that point. But this provides a short circuit strength. This provides the protection scheme with high enough capability to protect the grid or to intervene for the protection scheme. But this does not only itself provide the reactive power capability itself in terms of reserve. If our machines or power plants synchronous generators are operating in the higher limit at the same short circuit value, in case of any motor start, FDVR kind of fault induced delayed voltage recovery case, or if we need some reactive power jump in the grid level, so these machines cannot provide this overshoot or high reactive power during that transients, because even it has a short circuit level too much, it is capacity or capabilities already to utilize. So one of the way that we can indicate or quantify this capacity is the QV curves, as we mentioned. So we can just plot the QV curves here and identify the weak grids, and depending on the shape of this curve, which type of topology or technology we can support, we can implement here. So the result could be, the result can also identify the incremental impact of the solution here. If we implement STATCOM, if we implement SVC, or if we implement just switch shunts, if the curve is shaped shaped enough to provide the PV or QV point to shift, then we can also decide some tentative indications here, quantify the incremental benefit here, and we can do some pyramid or principal design or decision as per these PV and QV scanning stage. These are all analysis and simulation approach that may support or complement the exact real-time dynamics transient simulations. If we don't have accurate model, or if we don't have the accurate scope of the model with the interconnection points, maybe wide range of points, or there could be some parts that our loaded R or regions network is not represented good enough, then the case is very practical here that we mentioned. The incremental change analysis could be beneficial here. At least it indicates the weakest points. We can identify a group of weakest points, then we can focus on these specific points with the detailed analysis. So
sorry to interrupt. Can you wrap up in 2 minutes, because we are already over time?
Okay, I'm just trying to get quicker. So as I mentioned, and also mentioned, the reactive power issue is not a new one, but it's a very classical basic problem, but it's emerging. So there are many typical solutions for that problem. Those all have contributed to a similar purpose or same purpose, but in different ways. So the generator AVRs are the basic ones, especially for the synchronous generators. If I have the rotating machines, so we try to benefit all of the features it has. So it has overload capability, it has overshoot capability, it has short circuit contribution, even it has some oscillation damping capability with some large inertia, and the first inertial response is also good here. So we will be using these synchronous generators as much as possible. Even for some countries have some experience, they are just replacing or rehabilitating the aged thermal power plants, just dismantling or separating the turbines from the generators and converting them to synchronous generators, synchronous condensers, which also provides this service in the grid without any fuels or mechanical prime mover at the backside of the power plant. And the STATCOM and SVC are the similar, not same, but they are the power electronic based devices. They have fast dynamic supports. The main difference among these are the SVC has the voltage dependent support. If the voltage is depressed, SVC's reactive output is depressed also. but STATCOM does not. I mean, STATCOM has more wide range of regulating capability. It's a power electronic device. It's very fast in response in a couple of milliseconds, and it supports reactive power is similar to synchronous condenser, but we do not have synchronous rotating inertia kinetic energy stored in STATCOM scale here. So inverter plants are PVs or wind power plants. They are coupled to grid in inverter structures, and if they specified in the grid codes or in the technical specification, they can also simulate the similar contribution for the synchronous generators, but it should be specified and tested during commissioning in the site real practical case. Tap changers, similar to transformers, they can regulate the voltage in slow response. These are switches. They can regulate the voltage, reactive power flow also in a couple of 10 seconds, but it should be well coordinated with the real-time operation of SVC and STATCOM. So the optimum reactive power flow solution should be implemented with these different time response machines. And shunt device could be with breaker or not. We can also add them to the line itself without breakers. So once the line is energized, it's energized or not. But we can also add it at breaker if the daily load curve and the generation fluid dispatch curve is very complicated or getting more frequently changing. We can also add breakers in this shunt device to make it more flexible. But we shouldn't take the operation of breaker every hours in a day, so they have some life cycle. So maybe a couple of times in a day is more preferable. Next one, please. Yeah, we have similar problems or different problems in same grid regarding the Uzbekistan grid, wide range of long lines. So from east to west, we have some long lines. So they are generating or they are less loaded during the night or low load case, and long lines, then the surplus excess power, reactive power is occurred here. So we need some dynamic reactive compensation, even for synchronous generator maybe, or SV0 STATCOMs, but maybe not the shunt reactors itself only enough for this solution at this point. And for the Verganavala or Tashkent cascade, we have general highly loaded scenarios or case localized in the other part, east part of the countries, highly populated areas. So similar problem approach from the negative side. So we still need some reactive power regulation in dynamic manner. Maybe it's more dependent to load curves in the daily operation.
Mehmet, I need to stop you here because we are already went a little bit over the time. So, the rest of the slides basically summarizes under the different characteristics of the existing participation countries. There are different characteristics of the voltage issues that has been experienced throughout the season and the different operating regimes. So that is one of the key issues. And another, let's say, the key thing that I can add on top of that in brief. Well, definitely voltage is, let's say, a local issue, but at the same time, especially for the interconnected systems, the consequences are shared together. Any, let's say, voltage triggered or let's say overall system issue can be let's say experienced in the neighbor let's say bus bars. So also the issues in terms of the reactive reserves, shared reserves, is it also another important aspects, especially for the interconnected regions. For Central Asia power system, we have the CDC Energia that is like managing different perspectives of the overall dispatch operations. But I mean, a local issue, a local problem, which has also, let's say, overall impact into the interconnected system. So that was one of the also messages. Thank you so much, Mevlut. At this stage, we have a poll that we will also be asking small questions to you. And then let's move on with that. We will have around 90 seconds to respond to both of the questions. So, dear participants, can you have access to the poll right now? Because I'm not seeing any responses in the box. So basically, the first question is about which of the, let's say, options in here in terms of the warning signs observed in your, let's say, systems, especially is observed in the, let's say, dispatch center. So long distance reactive power transfer issues across major corridors, 500 kV corridors, basically, that can be one option. Heavy reliance on the static shunt compensations during especially the export periods. And another, let's say, potential issue is about the tap changers operating near their limits, and they are very frequently, let's say, operating. Another issue is in terms of the voltage fluctuations during the especially high solar generation hours. So that's also another issue. Slow voltage recovery following a fault is more on the dynamic side of the things. And another issue might be the unexpected inverter disconnections while the voltage remains within the, let's say, expected range. So that's about the first question. You can select multiple of those. And the second one, you can, let's say, briefly mention with a few words which area of your grid presents the greatest operational concern. And I will wait for another 60 seconds and then. Okay, thank you so much, colleagues, for participation. So let's move on with the presentation of MIFID. MIFID, give me a second. I'm reflecting to the screen. I think it should be visible right now.
Yeah. Can
MIFID,
you
the
hear
floor
me?
is yours. Yeah, we do.
Yeah. Thank you, Gökhan, and thanks, Mehmet, for the introduction. I will continue with the tools in our power systems in order to control the voltage and the reactive power. What I'm going to present, it's not going to be specific to any vendor, manufacturer, or kind of the developer. It's going to be a broader view to complete the picture what Mevlüt showed. So, of course, in power systems, we have voltage and frequency to control. And for the voltage, we have such kind of binding constraints, as you can see in the table. You can say it's kind of the source of the problem. So first one, you can say high voltage at light load. We are having this most of the time on the night or kind of when we have some light load conditions. So in this case, as a local phenomena in that area where the light load is there, There could be, depending on the planning or kind of the operational issues, some high voltage or kind of excess reactive power. So we need to absorb this reactive power. We need to kind of compensate it. For the technology part, as all you know, probably the reactors we have to, as a basic element or kind of the fundamental tool, directly consume the reactive power. They are simple, of course, cheap, but sometimes we need control. So if it is according to the power system analysis that you found that there will be a reactive power consumption absorption issue most of the time in your system after running yearly or kind of daily analysis, hourly analysis, then you can fix the reactor and it's okay. But if the voltage variations, depending on the load conditions, renewable generation or other type of loads, then you need to control. So you can try to analyze MCRs, the magnetically controlled shunt reactors. In this case, you have flexibility that control the reactors, and you can vary the absorption. Of course, when you switch to the new technologies, STATCOMs and SVCs are always there, even for, of course, steady state or kind of static requirements. You can use STATCOMs, SVCs. They are, of course, just for this purpose, it's expensive. And when we switch to another constraint, low voltage at peak, so then you need to, as reverse of the absorption, supply capacitors as similar to the reactors. You can install your capacitors fixed and you can control, you don't need to control them, they can be there, and you can supply your reactive power. Of course, you need to control the around the local area, the voltage variations, because they are dependent on the voltage values. And again, as an absolute kind of solution, you can say SVCs and STATCOMs, expensive ones, but you can use them. This slow fault recovery, I haven't seen it for, I don't know, some time. It is the opening fault-induced delayed voltage recovery. So what does that mean? When you have a fault and during the fault and after the fault, when you clear the fault, some of the equipments, most of the time the motor loads around the fault, if they became such kind of stalled and they are working like reactors and they are going to consume more reactive power instead of consuming active power also, they are not going to be working like this. So you would need more reactive power, but this is kind of fault induced. So if you don't do your analysis in detail, like the distribution side or the higher motor loads in a detailed way, then it could create this long-term voltage recovery, delayed voltage recovery. So you need fast controllers around. Again, it could be STATCOM, SVCs, or condensers you can include. Another thing, probably all you know, also not enough transfer capacity when you have the long lines. You need to control the flow and the impedance, of course. So the series compensation, phase shift transformers, or flexible AC transmission equipments, again, can be used. This is hot topic, the weak grid and low SCRs. I was also working a couple of projects in Australia. So if you have a weak grid and the connection point where the wind farms or kind of the other renewable generation, you should be very careful how you are putting the requirements into the grid, even for the fault right through. In, for instance, Australia, they have also other type of issues, problems like the multiple fault right through. So when the lightning hits the lines, it could create consecutive 15 or around 10 fault cases. So even if it is weak and plus such kind of extra stuff, you should control the voltage in this case, maybe not the reactive power, very fast and sustain also the renewable generation. So synchronous condensers, one of the important kind of the equipments. They could be expensive or kind of you have to find a place for them to use. In Europe, I heard, I didn't work directly, but all thermal power plants called power thermal plants, they can convert them to the synchronous condensers. Or in Denmark, again 10 maybe more than 10 years ago, the inertia response issues had been studied, but later the Energinet, the operator, decided to install synchronous condensers in order to both the inertia issues and also the voltage control issues. They selected that technology. So this is up to you, up to your system, and up to your, of course, budget, how you would like to control and for the future, let's say, expansions, what you are aiming. No operational visibility. Yeah, if you cannot see, you cannot control. The real-time margin, in this case, important. Online monitoring inside the EMS or the SCADA systems becoming more important. Just addition to this, I checked also recently. Of course, there is a market for active power frequency control studies, but even right now, not for the reactive power or the voltage control issues. UK is still, I think, trying to develop such kind of a market for the reactive power and voltage control issues. Next slide, please. So this is the, actually what I try to summarize is on the graph. STATCOMs less than 5 milliseconds, you can control your voltage and try to inject current even during the fault. Capacitors, of course, they are static. Even if you control them, you need time, and the voltage is important. It is the correlation with the V square. So how much reactive power you put will be depending on the V square. They are slow, and as I mentioned also, this fault-induced delayed voltage recovery will be there. It will take some time depending on your system. If you model the things in your system, this is a bit crucial on the distribution side also, then you will be sure, almost sure, that you can do whatever you want. So yeah, if you don't have anything, you will have problems. Next slide, please. So if we start with the kind of the latest or kind of the fastest one, STATCOM, the response time is less than one cycle. Range depending on the installation. They are more modular, flexible, so you can control them. You can integrate with the renewable generation also inside the systems. In again, Australia, I know the projects, both the STATCOM battery and also wind farms installed. Even for without grid cases, you can use the STATCOM together with the renewable generation plus synchronous condenser or other things. So how it depends on the system. As I said, if it's an off-grid, on-grid, synchronous grid system, you should be careful how you are doing the control and the design before installation, of course. Mainly the STATCOM, when you think it is a kind of a voltage source, but current control, it is creating the voltage using the IGBT elements in its system. And then when it creates the voltage, the current is controlled in the upper level. And when we go one more up, you can control the Q voltage according to your system. The DC voltage is important when you are doing the things. It is automatically controlled to DC voltage side to supply of course, create the voltage. Where it fits, if it is very a kind of weak condition, the weak bus, or if you have fast control, or if you need reactive current during the fault in order to operate the, let's say, the protection devices in a better way, it's important to use this device. Yeah, around, as I said, wind farms inside, you can use high voltage DC connection points. You can use depending on the, of course, the requirements from the grid operator. Since they are expensive, you need to control it. You need to design it very carefully and use it very efficiently after the installation. We can continue. SVCs, like you can think the Pira version of the STATCOMs more, it is thyristor control reactor, the impedance that you have, it could be reactor or capacitor. They are slow, maybe more than 20, 40 milliseconds, maybe around starting with 100 milliseconds, most of them. So again, if you have around voltage control issues and old technologies like high voltage DC, but LCC, not MMC style or kind of the new technology, you can use also this one because the around requirements, let's say the connection point requirements are not so fast. You can use this one. As I said, between the STATCOM, the differences mainly the speed. Of course, voltage dependency on this SVC since you are controlling the impedance. Cheap SVCs, of course, compared. But the installation, the flexibility and compactness, let's say, is better in the STATCOM also if you compare SVCs and STATCOMs. Again, you need to model the things in your system. Right now, as Mevlüt also mentioned, you are starting with, of course, static studies, load flows, short circuit, and afterwards RMS studies. But for these kind of SVCs, STATCOMs, and grid forming issues, you have to model right now the EMT models of the equipments, and then you can design looking at the harmonics or kind of other also issues in your system. Then you will be sure that this is my requirement and these are my requirements and this is my solution. Next slide. Yeah, shunt reactors and the magnetic coupled shunt reactors. Again, if you don't have speed and if you know your system is not moving so much around your controlled voltage point, you can use absorb the reactive power. Yeah, if you have a kind of light load cases in the night or in some special time on the year, most of the time, let's say in some with periodical, let's say, occurrences, then you can use this. If you want automatic switch or kind of before, you can use the static ones or you can use the controlled ones. And the next slide, please. Synchronous condensers, yeah, you can think no prime mover of a synchronous machine just for the internal losses it is consuming the active power, and the reactive power and the inertia are with the fault current, of course, supplied directly from the mass, the rotating mass of the machine. So this is a bit interesting, as I said, if you have old technology or kind of the decommissioned power plants, you can use them if it fits in your system to support and also increase the renewable generation capacity and also, of course, kind of the stable operating conditions. Yeah, I think you need to do, again, starting with load flow short circuit study, RMS studies for this. Maybe later also EMT study if there are some other IBRs, the converters around, you can implement, and you can look general view and see what is going on. Yeah, IMO, yeah, the operator of Australia. I haven't seen in my projects when I was working, but since the grid of Australia is more kind of focused on the east side, the Melbourne, the Sydney part, but in some areas for the mining purposes, they need to create kind of off-grid implementations. and then they need to implement the synchronous condensers together with the renewable generation plus, statcoms or other things depending on the needs. We can continue. Series compensation, it's a bit specific, of course. What we talk until now, it's more kind of controlling the bus with the shunt elements. If you have long lines, then you need to install the series compensation. This is more static purposes. Of course, after the installation, you need to take care the SSR, SSCI issues, subsynchronous resonance, subsynchronous controlled interaction issues. But this is more in the planning stage. As far as I know from Turkish system, we have kind of south east to northwest corridors. We have series compensations. So yeah, probably in Sweden also they have north to south corridors. They installed the compensations. We can continue. This fixed, I put, generic, you can think the flexible AC transmission devices. Phase shifters, again, you can control both the impedance and the angle in your, let's say, connection point or in your corridor. Then you will have more power to transfer, or if you have some oscillations, you can damp the oscillations depending on your needs. This is again more specific and kind of series connected devices. Actually, it is for all the tools that we talk, the more complex ones. You need to coordinate the things around. I mean, even if it is interacting with the power system stabilizers, you need to take care, or high voltage DC controllers, you should take care of these things. This is for, of course, for every complex or controlled element in your system. We can continue. Yeah, this is more like if when you are installing the lines, you can select in a classical way, like the ACCR type of cables, lines, or this HTLC cables. It is high temperature, low sec, kind of a special composite material conductor designed. I haven't seen in Turkey this one. I don't know HTLC, the implementation, but there, of course, when you have you would like to increase the temperature and you would like to get more power, of course, then, and low sec issue, you can install these elements, and with the weather condition, you can, of course, couple or correlate them. I know one case or couple of cases for wind farms. When the wind is high, of course, you are from a wind farm, you are producing more power. So the lines connected to that, even they are the classical one, the conventional ACSCR lines, together with the wind effect, you can gain some, of course, margin to put the power. But this is a bit critical, of course. You don't know when the wind is changing or kind of in the planning stage. You should be careful, but the technology with the HTLS, you can install at the beginning, of course. Then you can use them with your wind farms or kind of the solar farms. We can continue. I think we are coming to end. Yeah, online voltage. This is, every operator has its own control room, and the signals right now, I think, advanced, of course, control techniques also coming. The signals coming to the control room in EMS, in SCADA systems, and then knowing all these things together with the power system tools. Taking the snapshots, creating future scenarios, and running the scenarios, and applying to the SCADA system. It is, I think, ongoing, and it is very important when you have a kind of more converter dominated. We didn't talk in this webinar, maybe in the next, or I don't know when it will come. the data center issues also. So the data center modeling plus how to control and how to kind of sustain their somehow power consumption will be more crucial in the future, as far as I can see also. But yeah, you should monitor them in detail, all your elements or your tools in the system. Yeah, air grid, Swiss grid, probably you know also in Europe, all the Europe system can be seen in the Swiss grids and so is control room. So WAMS devices, wide area measurement devices, the installed places, yeah, very becoming more and more crucial for the future. Yeah, we can continue. I passed a bit my time probably, but yeah, this is the generic kind of comparison between the tools in our systems, how we are using the cost, lead time, footprints. You can see, but this is some of them you cannot directly compare, and because the need is important, the requirements. So if you need a fast response, or if you need a urgent, let's say, reactive current kind of things, you need to take care more the statcom or together with inertia synchronous condenser issues. So this is a bit giving a overview, but not exactly because of the needs and the requirements. Next slide, I think is the last one. Yeah. Yeah, we didn't mention about the batteries, by the way, but when the inverters, both the wind farms with solar farms and batteries comes into picture, together with the coordination of the tools that I mentioned, can be more effective and increase both the active power production and also flexible and fast reactive power control. Grid forming is still a hot topic. Models are available in some of the tools you can find to test them. Of course, the idea of the grid forming, you have a voltage, a magnitude, and angle, then you would like to control them like as a voltage source. But when you have a converter, you have limited capacity. You cannot exceed the converter's, let's say, overload current capacity and also the voltage, maximum voltage capacity, not like the synchronous condensers or synchronous machines. But it's a solution in a point that you can use after the analysis. Then for weak grid, you can improve. Yeah, they are entering the grid codes, but not directly applied. I know one project, Tesla battery project in Australia again. They implemented grid forming. But again, how to implement is one thing, where to control, how to control, but available for all the time or not, that's also another thing. Because when you have a grid forming, then you are saying that the voltage and angle and magnitude are responsible, the tool will be responsible, but you need to take care again around, and also for the frequency control issues, you need to take care again the coordination. Yeah, the catch, you should know your system very well. In order to do this, you need to know the models a bit detailed now, RMS plus EMT models, full picture, studies, future projections. AI helps a lot on these conditions. So you need to know, take the picture of the system very well, and plan for the future projection. You need to consider many things together with the modeling tools. You will be almost sure that the system is going fine. Of course, if new faults, kind of not expected or kind of things approached, then you can modify the things and continue to operate and also design your system. Next, or yes.
Thank you so much, Mukit. I think that was
yeah,
last slide.
Yes.
You have presented a good portfolio of different technologies that can help the system operators. And definitely some of them are like cheap, some of them are relatively expensive depending on the characteristics of the system requirements. So the shortlisting in this technical assistance projects will be very much also related to having a balance between the cost and the system, let's say, requirements. So thank you so much for that.
Exactly.
So let's directly move on with Jill's part. Jill's, the floor is yours.
It seems I cannot turn on my video. Okay. I get now the notification. Thank you. Thank you, Gohan, and thank you again, Mercy, for the invitation. Yes, so what I would like to discuss with you today in brief, of course, because I could speak during days about this topic. It's about stability of weak power system. And we had here inverter-dominated grids. So I spent basically my whole career developing new process, new models, and running studies for TSOs to deal with these new challenges related to integration of new technology into the power system. I prefer to mention new technologies, mainly, of course, power electronic converters, rather than really only focus on renewables, because now it has been mentioned in the previous presentation. We also have new types of loads where we have big data centers coming and also more and more HVDC interconnectors. So it goes also beyond the only renewable aspect. If you can go maybe to the next slide, please. Yes, so of course, we only have here a few minutes to discuss, and I want really to pinpoint key element of what I will call the impact of energy transition on the electrical system, and mainly with a focus on stability and dynamics. First, an important aspect is how do you screen stability margin? How do you have an idea of the stability margin that your system has? Because it's very time consuming to always run detailed dynamic simulation. So at early stage of a project, you need to have simple indicator that can tell you how strong is my system. And the most famous one, simply because it's very easy to compute, is the short circuit ratio. The problem with the short circuit ratio is that it has been used for years and years by transmission system operators, and it's quite accurate, but as long as your system is dominated by classic synchronous generator. So with classic thermal units or nuclear power plant, hydropower plant, but with rotating masses, I would say, that can provide high fault current. So why it was useful when the system is dominated by synchronous generator? Well, simply because classic synchronous machine, as it has been said previously, can provide high fault current. And so if you have a high short circuit ratio, it means you have in the vicinity high fault current, and direct translation, you have in the vicinity a sufficient amount of synchronous generator, so you know that your grid is strong, because synchronous generator, as mentioned, bring fundamental inertia, fundamental voltage control, and short circuit current capability in your system. But the problem is the following. When you move progressively with less and less conventional synchronous machine and you replace it by grid-forming converters, there is something that is missing here, because grid-forming converter, they can bring voltage stiffness to the system, meaning they can control the voltage, they can behave like a voltage source behind an impedance within the capability of the asset, of course, but they have very limited short circuit current. So if you keep in a power system that is evolving very fast, if you keep using the short circuit ratio, you will be misleading. At the early stage of a project, you might spot very weak area of your system, which are wrong because you have neglected completely the presence of grid forming asset. And also at the operational stage, a low short circuit ratio tells you, okay, you need to run dynamic simulation to verify this result. So you will run all the time dynamic simulation because the short circuit ratio will be very, very, very pessimistic, and you will lose a lot of time. So the main message here is really to highlight that we need to go beyond the short circuit ratio to assess the stability margin of a system dominated by power electronic converter and with a mix of grid following and grid forming. And I will discuss this in the next slide. So there are new type of screening indicator that arrives, and then you need, of course, to move to more detailed dynamic assessment to verify the results. Yes, please, next slide. So very, very, very important topic, but I guess everyone is aware. majority of the power electronic converter in our system today are grid following. Grid following simply means I measure through a phase lock loop the voltage at the terminal, at the point of connection. And based on this voltage measurement, I inject a current. Since I rely on the external voltage reference, each grid following asset needs a sufficient amount of voltage stiffness to behave correctly. Otherwise, you start having situation where by simply measuring the voltage, you change your current injection, and the change of this current injection at the point of connection will impact itself the voltage you measure, and you enter a positive feedback loop, which can lead to growing oscillations. Enter, of course, grid forming. First, grid forming is a completely new type of control, meaning it does not rely anymore on an external voltage source. It imposes its own voltage reference, meaning it can, in theory, be connected to a system without any synchronous generator. It will behave like a synchronous machine as a voltage source behind an impedance. Of course, not through physics, through control. So it's really a control design that has been just developed to mimic the behavior of synchronous generator, provide inertia, provide voltage controllability. And of course, most importantly, being stable even in low system strength situation. So of course, we are moving progressively with more and more grid forming converter if, of course, the technology is mature enough. And I just want to highlight that the Pursat battery in Cambodia is in grid forming, so you are already there. And this grid forming aspect is entering progressively the grid code, which is very important because if you are not making it mandatory through clear grid code or technical requirement, no developers will invest in this grid forming technology. So you need to have either incentive or either clearly translated into clear technical requirement to make sure new developers come with technology in grid forming. And also my last point, a limitation, of course, of this grid forming technology is that it's not mature for all the technology. Today, mainly, it's mature for battery because it relies on an energy reserve to work properly. And so battery, of course, very mature, and you can have, and also it's recommended to enforce battery in grid forming in the technical requirement in your own national grid code to make sure you will bring additional robustness to your system while limiting grid reinforcement and hence investment in your grid. Yes, next slide, please. So beyond this grid forming technology, it's also important to keep it clear on how to run accurate studies, because I have now more and more TSOs are facing large-scale system with majority of technology being power electronic converter, which is completely new. Power system back then can deal with a classic system with synchronous machine, and they were relying on classical software, classical tools such as load flow and root mean square, or we can also call that the phasor mode approximation to run large-scale dynamic situation. The phasor mode approximation, it's an amazing mathematical tool which allows you to neglect fast electromagnetic transient and rely on larger time step to solve your equations, meaning you can run large-scale dynamic simulation in a limited amount of time. So it's very useful for TSOs, but unfortunately, it relies on assumptions that are only valid in system dominated by synchronous machine, because synchronous machine have the capability to quickly damp fast electromagnetic transient. But when you progressively decommission this synchronous machine, while at the same time adding new converters which generate fast electromagnetic transient based on their fast control, fast switches, well, you are going outside of, let's say, the acceptable assumption for this RMS software. You need to move to more detailed software like EMT for electromagnetic transient simulation software. So there are multiple ways to screen stability through EMT. I have not the time, of course, today to explain everything, but important to do first screening using adapted screening tool, of course, so that you can already reduce the number of scenarios to assess in EMT, because the catch, of course, that EMT will take much more time to run for the same system simulation compared to RMS. So you need to reduce the number of scenarios to study in EMT through advanced screening indicator, and you can also use EMT to run impedance-based stability analysis, which allows you to easily detect if there are potential risk of interaction between multiple electronic converters and the grid and some converters, which cannot be captured by RMS because it's only valid for slow dynamic phenomena, typically electromechanical dynamic phenomena coming from a synchronous generator. In addition to that, using EMT is one thing, but it does not mean that because you use EMT, you are accurate. To be accurate, you need accurate models. And the message here is that it's very important to make sure you get vendor models which have been properly validated. Because only getting vendor's model without any validation makes no sense. I prefer you use generic models, but getting vendor models that has been properly validated to hardware in the loop test, to on-site testing, and most importantly, after some event, if you get some recording, some measurement, you can check, okay, as this asset respond as expected through my simulations, then you have a proper validation and you are sure that you run your studies on accurate EMT models. Yes, next slide, please. Yes, so there have been already a quite extensive and nice overview of all the technology that exists to control the voltage, I would say. Here it's really what can TSO do to increase their stability margin, in other words, increase their system strengths. Well, there are mainly two assets. We discussed already, it's the STATCOM, but I will insist here, it's grid forming STATCOM, because classical STATCOM are still relying on grid following control, meaning, okay, a STATCOM can provide reactive power reserve, fast voltage control, but it's effective as long as the grid is strong enough. So it's not okay. You need to move to what we call eSTATCOM, where you will have oversized capacitor to store the minimum amount of energy to make sure the asset can work properly in grid forming mode and provide fast voltage controllability. Then we discussed also, you have the synchronous condenser, completely different technology, rotating masses, very similar to synchronous generator, provide real inertia. So if you need big amount of inertia, maybe better to go for condenser, and can provide high fault current. So basically, there are no better candidate. They are complementary, and it depends on your local system needs. If you need a large amount of inertia and if you need a high short circuit current to make sure the protection works properly, better go for condenser. If you have limited footprint, but at the end you just need fast voltage control, voltage source behavior in the vicinity of some grid following asset, go with grid forming STATCOM. They are a bit complementary, and again, detailed dynamic studies are needed to decide which technology is better than the other for the specific system needs. Yes. Okay, so now it was a bit the theory. What is important, what I would like to go through with you is two specific case studies. So this one, probably everyone knows about it, is the Iberian Peninsula blackout that occurred already more than a year ago. So time is flying, but for which lessons learned are very, very important. Two main messages on this slide. First, it's the worst European blackout in 20 years. Why we say worst? It's not specifically linked to the amount of lost power. It's more linked to the time it took to go entirely black. Only 84 seconds, less than 2 minutes, complete blackout. And the third message, the most important one, it was a voltage event, meaning the root cause of this blackout is voltage issue, over voltage issue as you will see, not a frequency or inertia issue. Frequency is the consequence of the voltage issue. Yes, we can go to the next slide. And of course, what I will tell today, it's really based on the official report that has been published in last March, yes, by ENSOE, a big report with almost 500 pages, 49 experts. So it's only real facts. I'm not inventing anything or interpreting anything here. So what is important is this 84-second voltage, as we discussed, is very local variable, but also it varies very fast, while frequency can vary slower if you have, of course, sufficient inertia. What is important to highlight here is that already before the event, the voltage was high. And we will come back after that when I will explain in more detail. The voltage was high because the grid was slightly loaded. You had a lot of PV production. And also, unfortunately, in the morning, some inter-area oscillation were visible. I will come back to that later. That leads to some, let's say, mitigation actions, bringing again the voltage higher. Unfortunately, at some point, the voltage was too high. And because some or improper protection settings, some units start tripping. But the problem is that when you start losing units that were themselves controlling the voltage and absorbing megavar to make sure the voltage is not too high, you enter a positive feedback loop again, and you get this acceleration of voltage increase because losing MVAR capability further rise the voltage, leading to other tripping, further rising the voltage. Then it's the cascading impact. The voltage is rising very, very fast until, of course, you reach a breaking point where all the unit trips, you are separated from the rest of Europe, and your system go black. It's a collapse. Yes, you can go to the next slide. Yeah, I think it's a bit what I have explained. What I think it's important here to highlight is again you see between 12:32 and 12:33, 24 seconds is the complete separation. So in 84 seconds we go black. So I think again quite scary. Hopefully the operational rules will be updated fast enough to make sure we will not face that event in the future. But it's really the first big trip. So first big trick, meaning it was a transformer that tripped because of protection, over voltage protection, that has led to the loss of MVAR capability. But MVAR, when you are in an over voltage situation already, MVAR is so important to keep the voltage control and below this critical threshold that if you lose some, you start having trouble. And that's really what happened. You have the first big trip, then the cascade, then the separation. Yeah, we can go to the next one. So that was really also an important message of the report. It's that it's a bit of a bad luck, if we can say, because in this specific morning, first, okay, it was low load condition, clear sky, meaning a few machines online, meaning a few assets able to control the voltage. The grid is lightly loaded. A grid has never been designed to be lightly loaded. If you build transmission corridor, you expect them to be loaded, otherwise you are over-investing. But with the energy transition, more and more distributed generation, mainly rooftop PV, we are facing situation where the grid is no longer loaded at all, leading to over voltage because a lightly loaded grid is capacitive. At the top of that, in the late morning, they start seeing oscillations coming from first converters, then from a well-known inter-area mode between Spain and the rest of Europe. Then, as always, it's not new. The operator, what they do, they follow the book, and the mitigation means that they need to apply facing these oscillations. They were reducing the flux, the export of power from Spain to the rest of Europe, which decreased the angle difference and damp the inter-area mode. But more importantly, they have disconnected a lot of shard reactor. So shard reactor is very simple asset able to absorb reactive power, so very useful in terms of over voltage. But unfortunately, in the, let's say, guidelines, when they see this inter-area mode, they are anticipating a risk of low voltage because of dissociations. The voltage oscillates, so at some point it can reach low value. And to anticipate that, they manually switch out switch shard reactors. And so you understand that the pre-existing condition were the worst possible. Lightly loaded grid, and on the top of that, they are disconnecting reactors, which means we are further reducing the reactive power margin, and the voltage is rising again. And unfortunately, at some point, the voltage reach unacceptable value at some point of connection of some unit, PV or classical synchronous machine, who tripped because of a bit too thin protection margin, leading to this cascade and acceleration effect that I discussed in the following. Yes, please. So it took a lot of time, of course, to understand the mechanism that have led to this blackout. Not that I explain, it seems simple, but trust me, it took a lot of time to the expert to go step by step into everything that happened, every decision that has been made by the TSO, what were the predefined control mode, predefined protection settings. Well, a huge amount of work. But one of the main key message I would like you to take home is root cause one of this blackout. It's really a voltage control aspect. And it's a good news, actually, because voltage control means software. It does not mean any additional hardware needed to cope with that. It means that if the voltage control would have been better, more dynamic, more able to respond dynamically to voltage variation, maybe this blackout would have been completely not there. The first thing is the manual switching. I mean, at an era where voltage is moving very fast, we have more and more situation with more and more power electronic converters, renewables, meaning that the voltage is less and less stiff, it can move a lot. Manual switching of shot reactors is no longer acceptable. You absolutely need, it's too slow basically. In 84 seconds, it was too slow to take the decision, to click on the button and to make sure the shot reactor will be back on time. You need to have something automatic at the point of connection of the shot reactor that will measure the voltage. And if it goes outside of some margin, but you automatically disconnect or connect the shot reactor. It's the first lesson. Then, unfortunately, majority of renewable plants, mainly solar plants, were in fixed power factor mode. But what does it mean? It means it does not respond at all to voltage deviation. At a fixed power factor, the reactive power will only be adapted based on active power. And one of the accelerating impact of this overvoltage was that, okay, yes, when they are overvoltage, some PV plant have an automatic control where they will decrease their active power in feed. Don't ask me why. I think it would be much smarter to decrease the reactive power, to play on the reactive power to better control the voltage. But that's a bit the old generation of solar PV, let's say. They decrease their P in feed. But if they are in fixed power factor mode, it means they will also decrease the reactive absorption. And decreasing your reactive absorption in a situation of overvoltage, it's of course not the good direction, right? Another aspect that has been observed is that a lot of synchronous machines, unfortunately, did not deliver as expected. When an asset connects to the system, it needs to be compliant to your technical rules, to your national technical rules. And I don't know if it has not been properly checked or if it was something not well behaving at the moment, but the situation is that big machines that we would have expect them to absorb a lot of megavar were really, really below the target. So it's important, of course, to make sure when a new asset connects to the system to do what is necessary to test, to validate that it's compliant with the technical rule. And now you have the thin margins. So for me, it's not really voltage control related, this thin margin. It's more protection related. So it can be put in another root cause, but whatever, the message is the same. It has been, it's a bit contradictory, but in the Spain grid code, it is allowed transiently to operate the voltage up to 435 kV, which is very big, transiently. So you cannot stay like this forever, of course. But at the same time, you have generators who disconnect if the voltage reach 435 kV. So there is a problem there. You cannot tell the TSO you can operate transiently your voltage that level if at the same time you know that at that level some machine will trip. So this is what is behind this thin margin message. It's really important to have sufficient room to make sure that when you reach this high voltage, that the machine that can allow you to decrease the voltage remain connected. So you need to either increase the protection settings or just say, and uniform that across Europe, but let's not operate any more voltage up to 435 kV. For other European countries, it's most of the time 420, 425. Yes, next slide, please. Yes, probably one of the most important message of the Iberian blackout. So They are only important message, of course, but if you need to remember something, this is the one. Spain actually had everything they need in their end to cope with the blackout. They had enough reactive capacity. But because, as discussed, if you want to know the numbers, it's simple. They have 4 GVRR of shot reactor, and 2.7 GVRR were not used, were out of service during the blackout. Imagine if you would have been able to connect everything, I'm not sure we would have seen such high voltage, and probably the blackout could have been avoided. Reactors were available, but because of the operational process, manual, take some time, and because of the pre-existing oscillations, unfortunately, that had led the TSO to disconnect some of them, we were really in a bad situation where in 84 seconds, it was impossible, no time enough to reconnect and make sure that the shot will be there before the collapse. So they had the capacity, manual action worsen the situation because, as I said, better to have something automatic and fast. So the capacity that cannot be activated in time cannot be considered as actual reactive capacity because it's like it's not there. And so now the fix, no surprise, as discussed already, let's automatize this. Let's make sure you can monitor the voltage in real time and automatically connect or disconnect the shot reactor in a limited amount of time. Yes, next slide, please. So there are, let's say, some link to be done with this blackout with some of the system. First, the message is it's not because it happened in Spain that it will happen everywhere. Every system are different, but the mechanism that has led to this blackout, that is something that can happen everywhere if it's not properly dealt with. So for Uzbekistan specifically, I've learned that you are facing during night, so no PV during night, but lightly loaded grid, meaning your grid is capacitive and you can have overvoltage situation. It's important to already for you to check the settings of your shot reactors. If not enough, maybe add new shot reactors, but at least for the existing one, make sure that you can have something automatic that can connect or disconnect them fast enough to cope with this overvoltage. For Tajikistan, the problem is most of the time the opposite. But okay, regardless of over or under voltage issue, if you don't have a proper control mode for your converters, and with more and more converters entering your system, it's important. It will be the same because in terms of under voltage, if your converters is tuned in a proper way, it will be able to inject reactive current to the system to bring it up. In terms of over voltage, it's the opposite, but it's the same principle. You need already quick fix, quick check. Look at the asset, do a list of your asset, big asset present on your system, and make sure that they are in a proper control mode and that they are able to dynamically change the reactive set point in response to voltage deviation. For Cambodia, it's actually the closest match because most of the time you have low strength system, invisible rooftop PV, and majority of grid following fleet. Which is a bit three, I would say, ingredient that were quite central in the blackout in Spain and Portugal. But as I will explain later, there is already immediate action that you can take, easy check to make sure that the control mode or is handled the connection, disconnection of shot reactor in your system is going in the right direction. And if not, do a kind of gap analysis and take appropriate action to update it as fast as possible to avoid this kind of very fast voltage rise that can lead eventually to system issues. Yes, next slide. Okay, so it's another study case, completely different. That's why it's very nice. We are not discussing about blackout here. We are discussing about a zone in Australia that has faced during 7 months converter-driven oscillations, for which the diagnosis and the countermeasure were very let's say, bad at some point, leading to a lot of money that has been lost. But let me explain in more detail. So here the major difference is that it's not a blackout, it's not a cascading effect, it's just oscillations, permanent oscillations that systematically appear when the system in the West Murray zone in Australia was losing a line after a short circuit. I think it's not really the short circuit who led to this oscillation, it's more losing this specific line. And the message here is that you lose a line, you increase impedance, you decrease voltage stiffness, meaning you have a higher voltage sensitivity. And as we said, the majority of grid following converters are because here it involves 5 big solar plants in grid following mode. Connected to a weak system, you will see oscillations. It's impossible because to not see oscillations, if you don't have enough voltage source behavior in the vicinity of this plant, if your grid is weak and you have majority of big converter, you will see oscillations. But the good news is it's an issue that can be solved with a minimum amount of hardware investment. Mainly only control tuning. That's the good news. It's software again, software related. The problem is before knowing exactly what you need to do in your software, you have a bit of a period when you cannot do exactly what to do, and the only thing the TSO, IMO, so the system operator, managed to do is by decreasing by half the power injection of this big solar plant, the oscillations disappear. But decreasing by half the production means, of course, decreasing by half the revenue of the operator of the plant. And I think for IMO, it represented millions of euros per day during 7 months. So can you imagine the amount of money that is involved here? Just because of software issue, not hardware issue. And now what I would like you to understand is that I expect in the future that a lot of TSOs will face similar issues simply because the grid is evolving faster than expected. And when an asset connected 10 years ago, he did proper study to make sure it will not, of course, destabilize the grid, but over a given operating range of the system. And most of the time, we are now entering period where the grid is going outside of this operating envelope for which the asset has been designed. And so the control is no longer adapted. It has not been tuned sufficiently robust enough to deal with weak grid, basically. So if you enter now a situation where your grid is weak, you need to do retuning, absolutely. The first step is retuning. Ask the vendor to do some check, to do some studies to make sure it can, only by software modification, sufficiently make the tuning more robust and make sure that this oscillation will disappear. Only when this is done, you can think of, okay, I have made my tuning the most robust I can, but still I see oscillations, then you don't have a solution that reinforce your grid. Either adding new lines, either adding new assets, as we discussed, gridforming.com or synchronous condenser. Yes, next slide, please. So yeah, kind of a takeaway. It's a bit immediate action based on these study cases that you can take with you. It's not easy, of course, but the first easiest things you can first start with is to check. First, check the control mode of your asset. Are they properly tuned to deal with fast voltage variation? If your voltage vary on a regular basis, intraday basis, it's not okay to have an asset that is in fixed power factor mode. It's no longer okay. It was okay 20 years ago. Today, you need to have your asset that can dynamically control the voltage. That's very important. Then check your protection settings and make sure that regarding your operational guidelines, what is the highest voltage I can face, and make sure that you have sufficient margin to not see asset synchronous generator or whatever that will disconnect in response to this high voltage, which can be considered as normal for the TSO. The second thing to check, it's also based on the control mode, but how much time does it take to trigger shard reactor? And probably if it's still a manual operation, it's too slow. So you need to think of what would be the next step. How can I automate this asset and make sure they will be able to automatically connect in case of over voltage? To anticipate this kind of event, you also need to run studies. And it's important, as I said, to use the proper software, EMT. With more and more power electronic converters and weaker grid, you need EMT. But EMT is not enough. You need to make sure you have accurate models as well. So to have accurate models, it needs to be vendor specific and it needs to be validated. Validation is very important. And of course, as we discussed, develop new methodology, new screening indicator also to assess in which cluster my grid is the weakest, in which cluster I need to pay attention to, where do I need to connect synchronous condenser. Before jumping into detailed dynamic simulation, which are very time consuming, it's very important also to have easy way to check the system trends. It's still majority of the time the short circuit ratio, but as I said, at some point it's progressively losing its accuracy, becoming too pessimistic because it does not account at all for the grid forming stabilization. Show the margin. So it's in orange, meaning it's critical and also very difficult to achieve. What would be ideal is to have this kind of stability margin indicator, stability margin simulation, whatever you can compute out of a computational environment, and have some margin in real time on the screen in the controls room to make sure that the operator have in real time the stability margin of its grid. And if it goes outside, let's say, of a green zone, he has directly an action that he knows he can do to bring it back to a safety place. Yes. Next slide, and I think it's already the takeaways. I don't know if you go with this one.
Thank you, Gilles. I mean, it's very insightful and useful. Indeed, I think probably one of the by chance, by let's say bad luck, the Spanish, let's say, blackout case has been showing the importance of the voltage issues to the attention of the TSOs a lot. So that was very useful. Thank you so much for that. And I think it was 80% like inertia issues, 20% voltage issues that was being discussed before that event. But right now, more and more voltage related issues are being discussed, and lots of technologies and also control modes and operational philosophies can help over there, the TSO. So thank you so much for your presentation.
Thank you.
Well, I think we had already passed our time around half an hour, but we have the three best power system experts, which have lots of things to share, so it's normal. In order to just save time, I would like to open the floor for any, let's say, questions. So in case you have any questions, you can raise your hand and we can give you the access to the microphone. Let me stop here and see whether there are anybody who is raising hands. We already received plenty of questions on the Q&A and also the chat box, around 7, 8 questions in terms of certain power system analysis, certain comparison of different technologies, grid forming inverters, the differences between grid inertia and FFR, fast frequency response. So you will be also receiving the answers to them as part of the follow-up of this webinar. But still, if there are any questions, please raise your hand and you can ask your question.
I see there is some question in the chat, so probably it was not in the Q&A box that have been popped out while I was speaking. So if no question from the audience, maybe I can already take some. I don't know what you think, Okan. Go on.
We have a colleague who has raised hand.
Yeah, let's go.
Bakhtiarovich, please go ahead.
Yeah. May I go ahead? Sorry. Or the one who...
The
yeah.
colleague who has raised hand. I'm just checking. Bakhtiarovich, please go ahead and ask your question.
Добрый день, коллеги. Спасибо за презентацию. Спасибо за информацию. То есть у нас в энергосистеме используются автоматики, которые предотвращают повышение напряжения, которые, например, на линиях, если есть реакторы, то есть автоматически включают, и этого, если недостаточно, потом отключают линию. А вот в Европе или у вас такая автоматика есть, и как принцип работы этой автоматики, вы знаете, вот как работает? Чисто по повышению напряжения работает или еще дополнительно какие-то условия должны быть для срабатывания этой автоматики?
So, dear speakers, anybody would like to take the question?
I can contribute here regarding the automotive or special protection schemes.
Sure, Mehmet, go ahead,
Very,
please.
very briefly. And normally, yes, we have similar special protection schemes in Turkey also. It's also required in NSOE regulations, but it's very specifically designed and used in very severe events that may risk the grid to collapse regional totally. Such kind of special protection schemes are designed in custom manner based on the grid specific topology and nature, and it monitors some different parts on the grid in a PMU base in GPS time synchronization. So it's not a typical relay differential distance, but it monitors and calculates some regional parameters. And in case of any event that triggers these specific case, then it trips some regional load or some regional generation. So kind of DFDT or DPDT or combination of these. So we have such automation systems, but main purpose is to avoid regional or total collapse in case of any large load or generation block trips or some severe events in the grid. So the answer is yes, we have, but these are all custom design and specific design, not a generic design.
Thank you so much, Mevlüt. Are there any other colleagues that has a question? Please raise your hand. Okay, thank you so much, colleagues. I think there are not any more questions. As I have mentioned, the already provided answers to the questions which are being executed throughout the webinar will be also shared as part of the follow-up to this webinar. And thank you to all participants and also our distinguished speakers for your, let's say, experience and knowledge share. So it was pretty useful. I think today we have a good understanding about the voltage control, reactive power and system strength issues, and also a practical framework how to evaluate these solutions based on the system needs and not, let's say, trying to concentrate on the technologies as well. In the meantime, there is a question before I close last minute. In a high VRE system with multiple location options, what methodology would you recommend for optimal placement of synchronous condensers versus STATCOMs versus SVCs?
Yeah, I can take this one.
Sure, Gilles, please go ahead.
So the major difference between synchronous condenser and SVCs, for instance, is that synchronous condenser will actually increase the system strength. but you might overinvest. If you only need reactive power capability, you might overinvest in something. So what I would recommend is to develop relevant indicators, like we discussed the short circuit ratio. But if you are interested, you can always contact me in LinkedIn. I will direct you with other material. But there are a lot of possible indicators that TSOs or system operators can use to spot areas where synchronous condensers are needed versus only reactive power margin. So it's something that is very useful because it does not need, at least at the first stage, to run thousands of detailed dynamic simulations. It's mathematical indicators that are quite accurate and which you can clearly spot local areas in your grid where either inertia, voltage stiffness, or only reactive power margin is needed. And then you have a clear idea, where do I need to connect what? I hope it addressed the question.
Thank you so much, Gilles, for the answer. Any further questions, colleagues? So another question. Can StatComs effectively prevent FIDVR events, or do they need to work in combination with other devices?
Yeah, I can comment as far as I saw from the literature. Yes, but not fully. Because yeah, it can detect when there is an low voltage event, and according to the controller design, you can push the reactive power, and you can prevent the event. But if there are other equipments or kind of uncontrolled, uncoordinated elements, it could create some other issues. So it should be, yeah, the speed is okay. It could fastly react, but with the coordination of the others elements, if there are, then it could prevent better. Or it depends, because the modeling is can understand, through modeling we can understand what could be the issue. But this is a bit tricky because this motor loads or kind of the elements could be in the distribution side, so it should be modeled in detail, and then we can later understand if the StatCom is enough or not.
Thank you. Thank you so much, Mufid. So that seems to be all. So once again, thank you so much to all participants from the participating countries and other countries as well. I have observed that we have participants from almost 10 countries, interestingly. Definitely with a strong presence from Tajikistan, Cambodia, and Uzbekistan. So thank you to all, and we will be letting you up to date for the next webinar topics. This is a let's say series of webinars that we are planning, 6 webinars. This is the second one. So we will be keeping you up to date about those. Thank you so much, and have a nice day ahead. Thank you. Bye-bye.